Hi, welcome or welcome back. In this video, we're going to run through an application of limits, which is continuity. So we have a very cool definition of what a continuous function is using limits. So this is saying a function is continuous at a point A if and only if f of a is defined. So that is a is in the domain of the function. I also have that the limit is x approaches a of f of x exists and is finite. Just means it's a number, right? We're not talking about plus or minus infinity. We have that it goes to a specific value. And as we remember from before, for this limit to exist, it needs to be the same coming from the left and coming from the right. So I got those two. And my last and final condition is that the value I get from this limit here has to be equal to f of a. So the limit is x approaches f of x has to be equal to f of a. So I can use that to show a function is continuous at a specific point A. Just a couple nice things about continuities. This is a theorem here. If I have two functions that are continuous at a point A, at the same point A, I can add those functions. Their sum will also be continuous. Their difference will also be continuous. If I multiply either of the functions by a constant C, that new function will also be continuous at A. Their product will be continuous and their quotient will be continuous, provided that this isn't zero on the bottom. No dividing by zeros. Couple examples of functions that are continuous at every number in their domain. The big caveat are polynomials, rational functions, root functions, and trig functions. And we do have another nice little theorem here about composite functions. So if f is continuous at whatever value g of a is, then this composite function, f of g of x, is also continuous at a. Okay, so let's look at a few example problems of how we can use that limit definition of continuity. So the first one asks us to use that definition to show the function is continuous. Here is my function, and I want to show it's continuous at this point, x equals 1. So we're going to go ahead and use this definition. If we can show this is true, we have proven the function is continuous at that point. So first is the function defined at f of a. So I'm going to go ahead and find f of a, which is just f of 1. So wherever I see an x, I'm plugging in a 1. 2 times 1 squared plus 4 times 1 plus 3 over 3 times 1 is going to give me 9 over 3, which is just 3. So it is defined at that point, and I also know that f of a equals 3, which I'm going to need later. So I have this piece, and I also have what f of a is. So now I need to see if this limit exists and if it equals f of a. So let's go ahead and take a limit as x approaches 1 of 2x squared plus 4x plus 3 over 3x. So I can use direct substitution here. So I'm going to go ahead and do that. 2 plus 4 plus 3 over 3 gives me 9 over 3 again, which is also equal to 3. So I have shown that the limit as x approaches 1 of f of x is equal to f of 1. Bingo, got continuity. If you need a little more convincing, we can go ahead and show it in the Desmos. So I can also see that this is true on a graph using Desmos once again, and I can see that the function is continuous at that point, 1, 3. The next problem I have here is one that I see fairly often, and it'll ask you to find a certain value of some constant in order to make this piecewise function continuous. So with a lot of piecewise functions, right, we might have one piece of a function, another piece of a function, and if they don't line up together, then it's not continuous, right? There's a jump discontinuity there. And this will occur at the breaking points of the function where we've broken it apart. So in order to make sure that that touches at this point, what I'm going to do is sub in this value of x because I want to know what happens right when this occurs. These are both polynomials. They're continuous for all real numbers. I'm not worried about anywhere else but here. I need to make sure that there isn't a jump. So I'm going to plug this in for x, and I'm going to set them equal to each other so I know that they meet up at that point. So let's go ahead and do that. So I'm plugging in 2 for x. So I have from here 2 squared, which is 4, times c plus 2 times 2, which is 4. That's going to equal 2 cubed, which is 8, minus 2c plus 2. So we plugged 2 in for x into both of these, set them equal to each other to make sure there's no jump discontinuity between the two of them. Now we'll go ahead and solve for c. So I'm going to add 2c over. I got 6c is equal to 10, and then I can subtract over that 4. 6c is equal to 6, which means c is equal to 1. Once again, I can show this in Desmos. Shout out Desmos. So as you can see, we have two functions here. This red one and then our purple one, and they meet at this point 2, 8. So there's no jump discontinuity with the c value we found, which was c equals 1. All right, last but not least, I did learn my lesson last time. We're doing a couple less practice problems because those limits were kind of a lot. So here we're going to do the same thing, but now I have 3. So we're escalating a bit, right? I have 2 unknowns, k and c. If I have 2 unknowns, that means I need 3 equations. So I have 3 different pieces, if you will, of my piecewise function. But I'm essentially going to do the same thing. So I will use 2 plugged into this one, set it equal to 2 plugged into this one. Then I'll use 3 plugged into this one, set equal to 3 plugged into this one. We'll set ourselves up a system of equations and we'll solve from there. So this first piece, if we notice, I cannot just plug in 2, right? I'd get 4 minus 4, 2 minus 2, 0 over 0, indeterminate form, no go. So what I'm going to do is I'm going to factor first. So the top there is actually a difference of squares. So x plus 2, x minus 2 over x minus 2, our favorite part, we get a cancel. And all I'm left with is x plus 2 at x equals 2. I would have 2 plus 2, which is 4. So I'm getting 4 up here from this piece. Now I'm going to set that equal to 2 plugged into here. So I got my 4 from the top. From the second function, we're going to get 2 squared, which is 4k minus 2c plus 3. I think I'll go ahead and clean it up, just combine my like terms. I only have the constants that are like terms. So I have 1 is equal to 4k minus 2c. So this will be equation 1. So for our next equation, we're going to use the 3. So I'm going to use 3 into this one, 3 into this one, set them equal. Let's do it. 3 squared is 9k minus 3c plus 3 is equal to the bottom one there, 6 minus k plus c. Go ahead and clean this one up as well. Add over the k, subtract a c, and move that 3 on over. Awesome. So then I kind of look at them and I see what do they have in common. By the way, this is equation number 2. So we're going to see how we can combine these. I can use elimination or substitution. I prefer elimination typically. So I'm going to do that. I can see that the c terms are pretty close. All I have to do is multiply equation 1 times a negative 2. And then we'll get something that we can work with. So if I multiply equation 1 by negative 2, I get negative 2 is equal to negative 8k plus 4c. And then I'll go ahead and add that to equation 2 in order to do my elimination. Our favorite part again, canceling. That's the fun part about elimination. So those are gone, and I am left with 1 is equal to 2k. Uh-oh, it's going to be a fraction. Who picked this? All right, so I got k is equal to 1/2. Nobody likes fractions. And now I need to find c as well, right? The problem wanted me to find k and c. So I got a k here, and I am going to sub him into here in order to find c. So I have 10 times that 1/2 that we found minus 4c equals 3, which would give me 5 minus 4c is equal to 3. Subtract the 5 over, negative 4c is equal to minus 2. Oh my goodness. And c is also 1/2. Okay, weird, but that's all right. Doesn't matter. They aren't always the same. It just kind of happened with the problem I picked, which is fine. So both k and c in this instance would be 1/2 in order to make this piecewise function continuous. So I hope that that was helpful and a good little introduction to continuity. If you found this useful, please go ahead and like the video. If you'd like more in-depth one-on-one private tutoring, I offer that through my website, stemtutoring.net. I will, as always, post all these notes in the description box. If you have any other topics that you'd like me to discuss, please let me know, and I'll be sure to see you in the next one. Thanks. Bye.